Hey everyone, so I just want to finish off these slides. So this is going to be the last video for this unit. Um, it's going to be very short compared to all the other videos. So we'll start off with this, pause video, work on stuff, we'll go over in a second. Alright, now this was coming from a YouTube video of one of the kids at some camp where they had a big pillow. Kid jumped down and then launched another kid off the other side of the pillow up into the air. And these were some approximated numbers. Now, you need to be very careful with how we plug these numbers in. So, for example, here, first I'm going to just put 0 and -10 here because, again, always true. They say the phrase maximum height of 10 meters. So that means D is going to be 10 and VF has to be 0 because this is a max height scenario. Once again, I'm going to put this in to remind myself that this is half of the path. Now, I'm not going to put this number in right away because this is the total horizontal displacement. So I'm just going to leave this as is. They want to know the magnitude of the kid's initial vertical velocity. So using this, d, vi, vf, a, t, only equation that comes to mind is the timeless equation. Again, majority of the time, this is the one you're going to be using whenever they say max height. Vf is 0. Vi is what I'm looking for, plus 2 times -10 times 10. Taking the square root, we get that the initial velocity was 14 meters per second. All right, and that's it. Now, they don't give us any angles, so there's no other way for me to find the horizontal velocity except for using this number. Now, once again, I have two different ways of doing this. I can remake the chart where instead of having it set up to talk about only half of the path, I can talk about the full path where it goes up and down. Since I'm looking for, I know that the total path is 8.5, I can use these numbers to figure out the time. I'd have to make this be 0 since I'm looking at the full time. Find the time, use it in here, and find the initial velocity. Another thing I could do is use this original one, find half the time and double it in order to find the full time, and then do all this. Now I'm going to do neither of those. I'm actually going to do a simpler one. So I said before that these projectiles are symmetric. I've said this before that the reason why we can just double the time it takes to get to max height to get the full time is because of the symmetry. The amount of time it goes going up is equal to the time it comes down. This vertical velocity it goes up at is the same as the velocity it comes down at. This also applies to the horizontal distance. The distance it travels horizontally to get to the max height is the same as the horizontal distance it takes and travels coming down from max height. So if the full distance, horizontal distance, is 8.5, I can actually use 4.25 as my horizontal distance. That way it matches with this. The big thing that I try to convey is that whatever method you use when you're using the chart, you're always trying to make sure that x and y are referring to the same path. If y is dealing with half the path, x should also deal with half the path. If y deals with the full path, x should also deal with it. And you want to make sure that your numbers are matching that. Alright, so this is what I'm going to do. So I'm going to use VF equals VI plus AT. Now, I actually like doing this way rather than doing the full path, mainly because I kind of like to avoid using writing out the magic D equation in a case like this. Again, because of the the mouse and all that. So this would be 0, 14 minus 10t. So the time is going to be about 1.4 seconds. Again, this is half of the time. If we use this chart, we would have gotten 2.8 seconds. And you can check this out, that if we use this divided by this or this divided by this in the magic D equation, which I'm going to have to do here, we'd end up getting the same velocity. So again, I'm using my first chart. So 4.25 equals VI times 1.4 plus the acceleration is 0, so all that's 0. And I end up getting that the initial velocity is about 3 meters per second. Again, you can test it yourself if you made this chart, that this was also 3 meters per second. And that's pretty much it. So that was another thing. Again, you can take advantage of the symmetry for these projectiles. So whatever it was initially, that's what it is at the end if it lands. When we only do something like this, going only to the maximum height, obviously there's no symmetry. If you ever go into college or AP physics, you'll actually deal with questions that are asymmetric, where it starts here at the ground and lands somewhere between max height and the ground, or maybe it starts up high in the air and it goes up and then lands. So again, these are asymmetric problems. You would not be able to get away with using this method. You'd have to do some other things. Now, I want to go back and remind you, you're pretty much always wanting to make sure that you make these charts. The only time that you can get away with it is if it's a straight freefall problem or a straight vertical projectile problem. Otherwise, you have to make the chart and remember that something in both columns has to be 0, but it's only one thing that has to be 0. Pay attention to the wording. Acceleration in the x is always 0. In the y direction, d is 0 if we talk about the full path, landing at the same height, landing or caught at wherever it starts, landing at level ground, anything like that. VI is 0 in the y if it is a horizontal projectile or if it starts with a height. So if it starts at a height, then VI is going to have to be 0 because again, we don't do asymmetric problems. If it starts at a height, it's going to be going horizontally and then landing. So VI could be 0, in which case it's a horizontal projectile starting at some height, or VF is 0, in which case they say the phrase max height. Those are your three options. So even though I've said that there's 3 different types of projectiles, realistically, it's technically only, I said 3 different projectiles, each with 3 different scenarios. Realistically, though, it's only 3 different setups. Either your displacement 0, your VI is 0, or your VF is 0. And then if you have an X, whatever, deal with that. All right. Now, one of the other things that I need to talk about are some of the factors that could affect the angular projectile. So I went over the calculation, the quantitative part of projectile motion, but there's going to be a few times where you're going to be asked about the qualitative parts of angular projectiles, basically the concepts behind it. So, and I would say that about half the time you do angular projectiles, it's going to be one of these. So don't think that you're always expected to do calculations. Maybe I might be asking you a lot of calculations as practice, but on test, typically it's not super common. You might see one question where you have to break a velocity vector into its components and then plug it into a chart. Every other question, it's either going to give you the components, in which case they get plugged in straight into the chart like you would normally, and then you just treat it like a vertical or a horizontal projectile, or it's going to be something like this. So you need to know things about how changing the angle, changing the velocity, how those things are going to affect the range that the projectile goes, or the time in the air, or things like that. So here are some questions. Pause video work itself, and we'll go over in a second. All right, so the first one, I don't know how many of you might be able to figure this out, but the first one is pretty easy if you try to think back to playing around with a hose. Or if you play baseball or any type of sport where you throw something, thinking about what angle you try to throw at in order to get the greatest distance. Now, going back to the hose, what you can do is think about if you take a hose and you start lifting your arm up as you're spraying. You notice that as you lift your arm up, the water will start to go further away from you. But it gets to a point where once you start continue raising your arm, the distance will actually start to come back to you. And where the water lands starts getting closer and closer until when your arm is directly above you, it goes straight up. So initially, if you're shooting like this, it'll go like that. When you raise your arm up, it'll go up and then over further. And then if you shoot it directly up, it just comes up and down. So the angle that gives you the greatest horizontal displacement is actually going to be 45 degrees. Again, it's the symmetry. 45 is halfway between 0 and 90. And this actually leads into the next one, or not the next one, 46, which we'll get to. 45, they want to know the angle that gives you the greatest max height. Again, think about what you would do. If you wanted to try and throw a ball as high up in the air as possible, you're not going to want to throw it at a 45-degree angle. You're going to actually try to throw it directly straight up, which would be a 90-degree angle. So 90 degrees will give you the greatest height that that ball can reach. 46, so what two angles will give the same horizontal range? There are multiple answers for this. So there's 30 degrees and 60 will give you the same range. 20 and 70 give you the same range. 50 and 40 give you the same range, and so on and so on. So as I'm sure you probably figured out, 10 and 80, if the angles add up to 90, they will give the same range. So if they're, I believe it's called complementary angles give you the same horizontal range. Going back to 44, this is the reason why 45, well, this is one way to remember that 45 is the greatest horizontal displacement, because the only other number that 45 can add to get to 90 is 45. So it's actually the only number that doesn't have a complementary angle. It's its own complementary angle. So any two angles that add up to 90 give the same horizontal range. Their heights will end up being different. So if you shot something at 30 degrees versus 60 degrees, the heights that they reach will be different, but they will end up landing at the same spot. Again, it's because of the symmetry. The object will start going further and further. Once you hit 45, it starts to recede back by the same at the same rate. And 30 and 60 equally distant from 45, so they have the equal horizontal displacement or horizontal range. All right, so pause video work itself. I'll go over in a second. All right, so 47 asks what factors affect how long the object is in the air. There's a few things that we could say for this. One of them would be the angle. I didn't angle. I didn't mention this, but 90 degrees gives you your greatest time in the air. Again, if 90 degrees gives you the greatest maximum height it can reach, that means it has to have been in the air for as long as possible. Remember, the vertical direction is what's actually dictating how long the object is in the air. Nothing about the horizontal affects that. Horizontal values only affect where it lands, not when it lands. Some other things, the initial velocity also affects how long the object is in the air. In particular, it's actually VI in the y direction, but if you have something shooting at 10 meters per second at some angle, and then you increase it to 15 degrees but not changing the angle, you are still changing the vertical velocity. So as the initial velocity increases, then time increases. Another thing that could affect it is gravity, though not a huge factor. Um, Lower gravities would mean that the time in the air is going to be higher. So shooting something on Earth versus shooting something on the moon, uh, it's going to be in the air much longer. It's going to go up higher. It's going to do all that stuff because of the lower gravity. Some smaller things that could be factors, things like air friction, probably not going to come up. But typically, the lower the air friction, the more time it's in the air. Because remember, air friction causes it not to go as far or as high. So, lower air friction, higher in the air. Um, an initial height could also affect how long it's in the air. So, greater the height, call it initial height, then the more time it's in the air. Basically, affect anything in the y direction and it affects how long it's in the air. 48. What happens to the horizontal velocity as the object undergoes angular projectile? Nothing. Nothing. Remember, it's got zero acceleration, no change in that horizontal velocity. Doesn't change at all. All right, here's the next question. Can't really pause the video, but I'll do it. So, common mistake that I see people do is they realize I said before that when we have air friction, it doesn't go as high, doesn't go as far, and they'll just draw this and a projectile that doesn't go as high or as far. The issue is that the projectile is shot from here. With or without air friction, the projectile is still shot from here. So that makes no sense. Can I clear? Yes. So what you always have to do is you have to start at the exact same spot, make a parabola, but just make it so it doesn't go as high or as far. So, bleh, there you go, air friction. Doesn't even have to be proper. Realistically, it would probably go out like this, go towards the top, and then be a little bit asymmetric. But this is fine. In fact, as long as you start here, don't go as high and don't go as far, you get the point. All right, so just recap. 45-degree angle gives you your maximum range. 90 degrees gives you your maximum height, max time in the air. Complementary angles give the same range. And when we have air friction, the path becomes shorter and lower. Now, I want to mention, please don't get this stuff confused with the resultant stuff, the two-dimensional vectors that we talked about before, because you're going to be asked questions about both. 45 degrees and 90 degrees for projectiles are your important angles. 0 degrees and 180 degrees when it comes to vectors were max and minimum resultant. So make sure that you're paying attention to whether or not we're talking about the angle related to a projectile or an angle related to vectors. Here's the last question. Pause video, work on cell phone, go over a second. All right, really quickly. Here we have a baseball player hitting something with bat. What angle will result in the longest distance? 45 degrees. That's it. Easy peasy, lemon squeezy. That's it for the angular projectiles, and in fact, the projectile unit in general. So we'll be doing a little bit more practice stuff. Hopefully, separately, it should be pretty straightforward how to do this. But again, one of the biggest tricks in this unit is being able to juggle all the different types of projectiles at once. So you want to make sure when you're doing the problems that you're paying attention to what type of projectile we're dealing with. Ask yourself, what type of projectile is this? Is this a free fall? Is this a vertical? Is this horizontal or is this angular? And make sure that the way you go about solving it matches the type of projectile. Pay attention to the key words in the problem. If you have any questions, please let me know. Come to extra help, or you can send me a message on Remind. I'll try to answer them as best I can. Otherwise, good luck and have a great day.